so mitigation of environmental and hotspot issues on photovoltaic system. So basically in this presentation, we will focus on the strategies to mitigate these challenges, ensuring improve the efficiency and reliability of photovoltaic systems. So we will explore the causes of environmental degradation and hotspot issues, their effects on system performance, and involve innovative techniques to minimize their impact. By addressing these concerns, we can enhance the overall reliability of photovoltaic system, making it more reliable and also the energy source for the futures. So let's start to get into the details. So here it is the outline of the presentation basically. So first, background objective of the presentation: photovoltaic cell fundamentals, and result of we have just checked the two different types of experimental validation, and lastly the conclusion. So here we can see basically the increasing global demand for clean energy has positions the photovoltaic system as a crucial solution for sustainable power generation. So basically, so what is the outline of this presentation? So here we can see the peak power and energy deficit trend from 2001 to 2019. So basically, we can see the first of all, let us we have a look on the historical trend on the energy shortage and peak deficit in India over the last 2 decades. As you can see, both of these parameters were into order to 10 to 15% 2 decades back on the negative side, which has been reduced to fractional level presently. And as per the latest balance generation report, India is going to energy surplus country in future. Means it is reported by the Central Electricity Commission and Ministry of Power, Government of India, and these references had mentioned in the first PPT. So the India is also, but now has the Government of India made his the possible over the last 2 decades. So here we can see the trend of the energy deficit and peak deficit. And another is here we can see what is the trend of installed capacity addition over last 2 decades. So here four different types of the generation: thermal, renewable, hydro, and nuclear. So here we can see, if we look at this historical trend of the installed capacity addition over the last 2 decades, as you can see up to the year 2017, the increases in the total installed capacity was due to mainly addition of thermal power. However, since 2017, all the type of installed capacity addition was flat except the renewable energy. So renewable is basically in red color, and you can see from 2070 it is exponentially increases. So the renewable energy installed capacity was is approximately 70 gigawatt, which further grew into the 74 gigawatt by the end of 2019. Means it is the report published by the Ministry of Power, and it is published in 2018. But if we can just it is some old data. So also another report has been published. So here we can see the change in power mix from 2017 to 2018. So trend of installed capacity addition over the last decade. So the first A is indicating as on December 2018 and as on 2017. B is in on December 2017. So this will be more clear if we have look at the energy mix of the uh, 2017 and 2018. Let's have a more closer look on the energy mix as on December 2017 and December 2018. The total installed capacity uh, was here you can see the 333 gigawatt in the end of 2017 by grew of 354 gigawatt by the end of 2018, but there was no change in the installed capacity of thermal power. Means large hydro, nuclear, and gas, which gives only the renewable energy, excluding from the large hydro. So in this PPT, you can see the lot of changes in different sectors, but but there is a no change, a large change in the thermal power. And what is the bifurcation in private, state, and center? So here we can see the private is 46.1%, state is 29.9%, and center is contributing 24%. So it is the trend of the installed capacity addition over the last decade. uh, and Also we can see the breakup of renewable energy addition. So the increasing global demand for the clean energy has positioned the photovoltaic system as a crucial solution for sustainable power generation. So here, so you can see the different types of the renewable energy sources, means solar, waste energy, biomass, wind, and SHP. Means you can see the renewable energy technology to find out which technology contributed more in the overall increases in the installed capacity. As you can see, the contribution of solar energy is about 48%. The largest line is indicating the 48%, and followed by waste of energy, which was around the 21%, and biomass, wind, and small hydropower contributed around 7 to 8% only. The wind is around six to less than, SHP is less than less than 5%, or around 2 to 3%. And you can also see the year-wise breakout of the target 175 gigawatt by 2022. So it is also the trend of the capacity addition from renewable energy sources. So huge contribution from the photovoltaic energy was not a mere accident. You can see the here wise plan of install capacity addition of photovoltaic from 2015 to 2022, and government of India has planned to install up to 175 gigawatt of renewable energy by 2022, and out of which the 100 gigawatt is planned from the photovoltaic. Means the 175 is the total renewable energy, and only we can see the 100 gigawatt is from the solar energy. So government is also interested to increase the capacity of the solar power, power through the solar energy. So here we can see the global trend addition of the photovoltaic install capacity. So basically, this data is collected from the taken from the report IEA and BNEF report. The source is also mentioned in this presentation. So here we can see this similar is the trend globally. The photovoltaic installation is increasing exponentially all over the world. The expected cumulative install capacity from solar by end of 2019 is about 650 watt, 655, around 655 or 60 gigawatt globally. Hence, it is happening in India and throughout the globe as well around the photovoltaic energy. However, energy is thing about this technology may not be good. There will be some bad aspect which we will discuss in the later in this presentation. Basically, so here we can see the next is the motivation behind the research. So here we can see the here the component wise breakup of the photovoltaic module. So for particular this PPT, you can see the approximately 2% of the entire fleet are predicted to fail within 11 to 12 years. Means 2% of entire fleet or defects means 11 to 12 years. About 19 billion module can be expected to fail in next decade. So we can, you can imagine, it is a very huge amount of the module. Means you can say the waste. The failure at the infancy or at the mid life of the project has high impact on the cost of electricity, and higher impact on environmental, as PV waste management is still is difficult and is still in research and development stage. So it is also the source is given. So what is the basically the what is the scenario of the different types of the material. So here we can see the peak efficiency at different research scale. So here the photovoltaic PV technology has matured over the time since it first demonstrated by the French scientist Edmond Becquerel in I think 1839. The photovoltaic technologies evolved so far may be broadly classified in these two different categories: silicon crystalline and thin film. So basically, the subset of the silicon crystalline technology are monocrystalline and polycrystalline. The polycrystalline hybrid silicon and emitter wrap through the cell, etc. While the various type of the thin film technologies are amorphous silicon, cadmium telluride, and sulfide and copper indium galenite. So here we can see the maximum efficiency of the single crystalline and multi-crystalline. It is around the 25%. The most commonly used photovoltaic cell are monocrystalline and polycrystalline at commercial scale. Monocrystalline photovoltaic cells have better efficiency than the polycrystalline. The former cells are made for pure or doped silicon having the minimum impurities to degrade its semiconducting the properties. The peak efficiency of these technology reported by the various researchers, and it is given in the literature. Basically, so we have taken it is reported in the different published papers. So we have just summarized in table 2. So here table T is also here. So it is the single junction gallium multi junction cells, hot carrier cells, emerging PV technologies. So you can see it is the overall the efficiency at the different materials. And the broad classification of the photovoltaic technology. So here we can see the market share of the photovoltaic technology. So here you can see the 90% market share of the crystalline silicon. It is the 90%, and thin film is approximately 10%, and other is the less than 1%. So first generation, these are the wire-based crystalline silicon, and second generation, these are based on thin film photovoltaic technologies, and generally include three main families. First one, amorphous and micromorph silicon, and second one is the cadmium, and third one is the copper indium selenide and copper indium gallium. So, and the third is that they also include the concentrating photovoltaic, bifacial and organic photovoltaic cells. So here you can see the equivalent circuit of the uh, photovoltaic cell. So you can see it is the current, the source current IPS, and the load is connected, and suppose I current is passing through the load. So equation 4 is basically representing the equation of the general equation of the photovoltaic module equivalent circuit. It is the current is passing through the load. And here we can see the system design. Suppose here we can see there is a three different types of the means here photovoltaic cells are connected in series, and a diode is connected in between. Another subsystem, another cells are connected in series, and that is divided into different sections, and in between a diode is connected. So here we can see in a standard module there is the three diodes is connected, means we can divide. Suppose we have 60 cells, so we can divide in three different subsections, and three sections means in a for the 60 cells in a module, so we can divide means 20 20 20 means 20 in each subsection. In 20, in 10, in 10 are connected in series, in between a diode is connected. So here we can see it is the first one is the design of module, and second is the design of array. uh, Here you can see green is the color is indicating the bypass diode, and red is indicating the blocking diode, means that will protect the reverse current passing through the module. So it is basically the design of array. So here we can see it is the PV characteristic of a module. So basically figure 12 is representing the IV characteristic of a typical silicon PV cells operating under normal condition. The power delivered by the solar cell is the product of the current and voltage, means I into V. If the multiplication is suppose completed, then point for the point for all the voltage from the short circuit to the open circuit condition, the power curve is obtained for the given radiation level. And also with the solar cell open circuited, that is not connected to any load, the current will be, it is the minimum, means zero, means zero. That is the starting, the you can see in the characteristic means zero, and the voltage across the cell is at this maximum, means known as the solar cell open circuit voltage or VOC. Here we can see VOC. At this other extreme, when the solar cells is short circuited, that is the positive and negative leads connected together, and the voltage across the cell is at this minimum, means zero, but the current flowing out of the cell reaches is the maximum, and it is known as the solar cell short circuit current or ISC. The electrical power is measuring in watt generated by these different photovoltaic combinations will still be the product of the voltage time, means P is equal to V into Y, means however the solar panels are connected together, the upper right hand corner will have also be used. So basically it is the also we can define the fill factor from this characteristic. So here you can see the effect of the radiation. Second one is the temperature of the photovoltaic performance characteristic. So here in the first in figure 113A is indicating basically here watt per meter square. It is meter square. Square is missing. So here we can see if we can increasing the radiation level, so the same trend is coming. Means suppose we are increasing from 200 watt per meter square to 400 watt per meter square. So at this same trend is coming, the power is also increasing. But here we can see in the second case, means what is the effect of the temperature. So if the temperature of the environmental temperature is increasing, means here we can see if the temperature is 0 degrees Celsius, means early morning. So here, so maximum temperature, maximum power is coming, but temperature is maximum 80 degrees Celsius. So PV characteristic like this, means it is inversely proportional to the temperature. Power is low, so maximum temperature is maximum, the power is lower. So it is the variation of the temperature. You can also see that what is the, if the temperature is minimum, so the current is maximum. Here current is maximum. So it is basically the characteristic of the IV and PV characteristic in if the we are changing the variation of the radiation level. So here just we have collected, we have just generated the data, so we can just correlate what is the just we can eliminate the false positive data from the data sets. So here we can see, first suppose the temperature. First is the we are having the four different types of the three different types of the parameters here, environmental factors, type of the correlation. So first, open circuit voltage, suppose temperature, irradiance, dust deposition, and relative humidity. So here we can see that temperature is strongly negative with open circuit voltage. Means the correlation between the different environmental factor with the different performance parameter of the photovoltaic cell, based on the basically the literature, not just we have calculated. So the correlation between open circuit voltage and temperature is strongly negative, means the temperature rises from VOC will be reduced. And also we can take the next example, the correlation between the peak power and irradiance is positive, means if the radiation level is rises, then peak power will also be increases. Means we can check the importance of the variables with the circuit parameter. So first we can suppose the most of the researchers are doing the research, or PhD scholar is also doing the PhD research in particular this field. So my suggestion is to check before the application of sub optimization technique. First we can just check what is the false positive. Suppose the some strongly negative data is coming in your just your data set, so we can just eliminate, because that will not contribute. That is the in your optimization, that will the weight of that parameter will be negative, that will not contribute in your optimization technique. Means W1 into some parameter means that is the 0. So we can also eliminate the strongly negative parameter, means weight will be 0. So here next one, a result of the experimental study 2. So study 1. So here suppose we are in my presentation, we have just experimentally it has been generated some data, and that is the data set is the 36 data sets. Means we are just changing the four different types of variables. So here we can say it is the setup of experimental study. So here we can see, suppose we have first here we can see radiation level IR1, and it is the weight, means concentration level, and type of dust. We have just collected four different type of dust. First one is the normal dust, second one is the sand dust, and fourth one is the clay dust, third one is the clay dust, and fourth is the carbonaceous dust. So we have just spread on this. First we have just measure the data if the module is clean. After that we have just fixed the radiation level, suppose 200 watt per meter square. At the same radiation level we have spread the dust some particular weight. We have spread on this module, and we can just check the what is the generation. So basically In this, the photovoltaic panel was subjected to three radiation level here, the 285 watt per meter square and 360 watt per meter square and 415 watt per meter square here in this design designated as T1 to T4 has been studied which can be correlated with the specific geographical location of origin rather than by diameter, color or composition. So basically the matrix of this experiment design is graphically presented here. This matrix, the total 36 data sets are generated from this experiment. So the first dust is already means it is the normal dust, and second is the basically the sand dust, and third one is the basically it is the clay dust. Four dust it has been collected from the Dadri thermal power plant, means that is the carbonaceous dust. Means Dadri thermal power, I think it is the 1820 megawatt Dadri thermal power plant. So the different types of dust is three different types of concentration level: W1, W2, and W3. So means that is the concentration level 2 gram, 6 gram, and 8 gram we have spread on the module. So basically the experimental setup developed for the present work consists of the 4x4 matrix PV panel of the 16 number of silicon steel cells connected in 7 different configurations. But in this presentation only we have considered the series parallel. So here you can see the IV and PV characteristic of the clean panel. If the panel is clean, so what is the effect of the radiation? So first, a stage of experimental study impact of the 4 different types of aerosol, means dust, are studied for their impact on the performance of photovoltaic cells. The primary data generated from the experiment is present in the form of IV and PV curve. So open circuit voltage VOC, short circuit current ISC, fill factor, and peak power, means IV and PV characteristic are here presented. So we can observe that if the radiation level is increasing from 285 watt per meter square to 415 watt per meter square, means then the maximum power peak is also increasing. That means it is directly proportional to certain level of radiation level. Means here you can see it is the IR1 is basically 285 watt per meter square radius. Means here you can see the radius. If we are changing the radiation level from 218 to 415 watt per 415 watt per meter square, then you can check the peak power loss. Peak power is increasing. So here we can see if the IV and PV characteristic for, suppose we are considering the normal city dust. So IV and PV characteristic for normal dust, but radiation level and concentration level is varying from 285 to 415 watt per meter square, and also concentration level is from 4 gram to 8 gram. We can just vary. So this gives a fair amount of understanding of the comparative reduction in performance parameters with reduction in radiation level and increasing in dust concentration for each type of aerosols. So here we can just check the if we can changing the concentration level and radiation level, so you can see the characteristic IV and PV characteristic of the different. So here, suppose we can just change the dust. So it is the suppose in this case, second case, we are considering the sign types of dust. So you can just check the if we are changing the dust. So it is the IV and PV characteristic. And next type we can check the, suppose we are here considering the clay type of dust. So what is the IV and PV characteristic? It is just you can see. And fourth type, suppose we are here considering the fourth type of dust, means carbonaceous dust, means thermal power dust. So you can see what is the trend of the PV and IV characteristic. So next here we can see the primary data experimental study. So here four different type of dust. So here we can see these characteristics present the comparative impact of different types of the pollutant at different radiation level, means 415, sorry, 285, 320 and 415, means IR1, IR2 and IR3. So formation of two distinct cluster here, cluster 1, cluster 2. In these three, means the peak power loss in both the three different criteria. So in all the criteria, the cluster is forming the same, means the formation of two distinct cluster of pollutant can be observed in this figure with regards to their impact on the reduction of the peak power loss of the photovoltaic panel from clean condition. And also the dust type means T1 and T2. This is the T1 and T2, means T1 and T2, means construct the first cluster while dust T3 and T4 are forming the another cluster. The peak power loss output for aerosols with the same cluster is comparable for all three of the irradiance level, means it is the radiation level 1, radiation level 2 and radiation level 3. However, it will be the fascinating to note that the difference between the peak power loss of different cluster is observed to be wide. In absolute terms, the peak power loss is approximately here the 36 and 36 and 35%, 36%, 35 and 30%, approximately 30%. So the radiation level, on the base of the radiation level, we can just bifurcate. And in all the cases, the maximum power loss is observed to have the contributed by pollutant T4. That is as emitted by thermal power plant, closely followed by type T3, that is the clay type dust, means these are coming in the same group, means the highest peak power loss is the means carbonaceous ash dust. So after the generation of the data, we can just estimate what is the impact of the different dust. So which dust is more affecting to degrade the efficiency of the solar panel. So here we have just used the one methodology, data envelopment analysis, uh, to analyze the efficiency of the 36 data sets. So here we can just it is the flow chart is start. First we can just we have the 6 inputs and output variables. So it is very important to choose the accuracy of the input and output variable. And after the selection of the input and output variable, we can just generate all the alternative models for the fixed input and variable outputs. And after, suppose we have chosen the input and output and all the generation alternatives, then we can run the data envelopment analysis, means that will provide the relative efficiency of the system. But relative means simple DA model will produce the 100%, that is the 100% relative efficiency, that if the more than one DMU, decision making unit, is producing the means up to the 100% efficiency. So how we can bifurcate which one is a more effective in degrading the efficiency? So here we can just use the four to five different methods, and after that one method, means Shannon's entropy is the efficiency is coming less than one, means that is the most sufficient to bifurcate. So here it is the basically the data methods of the data envelopment analysis, means DA is an established tool to quantify the relative efficiency of a set of entities. Objective function means maximize, of which have multiple inputs and outputs, means the weighted sum of output to the weighted sum of input, means these entities are referred to decision making unit in DEA studies, and it is non-parametric technique, and hence it does not require awareness of the underlying productionness. Means the main advantage of the DA over the other type of optimization technique and benchmarking technique is flexibility in generation of weights and input and output parameters. So means due to the unique advantage of the data envelopment analysis has been applied to a wide spectrum of managerial, operational, and economical problem, both in public and private sectors. And basically in this presentation, the indispensable tool for the benchmarking studies in the many areas of researchers are using. The DA formation allow to each decision making unit to maximize the relative efficiency by obtaining its input and output weights as favorable as possible under the constraints, that is efficiencies of none of the decision making units. So basically decision making unit becomes greater than the unity when the assigned with the same set of weights. So here we can see after the methodology, we can just use the selection of inputs and outputs. The selection of inputs and outputs uh, play the very important role in benchmarking studies using decision making unit. So here we can see the choice of the variable depends not only on the objective of the analysis. Adopted methodology and technology requires of the chosen model, but also on the availability of reliable data. There is a no universal techniques is available for the selection of variable, means input and output variable. But in my analysis, we have chosen two different variables: radiation level, aerosols, and circuit short circuit current, open circuit voltage, and fill factor and peak power, means four different types of the outputs and two different types of input. So after the selection of input and output variables, the validity and reliability analysis is also important for accuracy improvement. Means we can eliminate the false positive data from your data set. So here we can just calculated the correlation between the output and input. So here in the table 4a, we can see in between there is the four different types of the output data set: y1, y2, y3, and y4, and two different types of the input. Means all the correlation are coming positive. Means suppose any correlation is coming negative, so that variable cannot be included in particular data envelopment optimization technique, because that will not be favor to provide the weights. Means that will provide the means zero weight. Suppose we are multiplying the zero weight and some value, then that will be cumulative will be zero. Means that means we can just consider only that variable which one is the producing the positive correlation. After the correlation, we can just calculate the regression analysis, means R square and ANOVA result. So here we can see R square value exhibiting the 52.3% of the variation in the open circuit voltage, and 54 means in short circuit current, 54.8% of the variation in the short circuit current due to the independent variable, that is the inputs. And validity of this model may be cross-checked by the comparing the R square and value with adjusted R square values. It is a closure may be observed between two, and all the F values means significance level are, you can see it is a less than 0.005, which implies that the chance of the variable following the random distribution are less than 0.5%. Mean we can also, in other words, we can say that it is the 99.5% chance of the data to be the correct, and which is expected to produce the realistic result. So here after the validation, we have calculated the efficiency from the three different techniques. First one is it is here you can see it is the CCR, means Chance, Cooper and Rhodes efficiency, and another is the Shannon's efficiency, means Shannon's, because it is obtaining the efficiency, means more than one DMU is producing the, means it is the 100% relatively efficient. So how we can say it is a more accurate, means how we can differentiate two are coming, multiple DMU are coming, thus producing the same result. So for this purpose we have used another technique, means Shannon's entropy method. So here we can see that different DA models were executed to find out the relative efficiency of the 36 data sets, and considering all the inputs and outputs collectively, the CCR efficiency and Shannon's entropy and complete ranking based Shannon's entropy of all 36 units are normal dust, are coming in normal dust. Means here we can see IR1, IR2, IR1. So are coming normal dust group, 4 units from sand group, and 2 units from clay dust group. Obtained relative efficiency score is around 1. So 3 out of 4 DA efficient units sand group attained frontier at lower radiation level. That is the IR1 for all three dust concentration level. However, none of the data units from the S group means as is not as from the S group there is no any single data set is coming on the frontier line, means the as as dust is reducing the highest reduction in the efficiency reduction in the carbonaceous dust. So we can just we can conclude basically the PV performance here. The conclusion, the PV performance is affected at least by sand at lower concentration and highest radiation level. Among all the dust type, impact of sand was lower under all environmental conditions. Performance of PV under normal city dust was poorer than sand dust but better than other two dust types. But the carbonaceous as impacted photovoltaic performance maximum. Means suppose we are planning, the policy maker is planning to install the thermal power, planning to install the solar photovoltaic plant near to the thermal power. So that will be very that is a very important suggestion to install the power plant near to the northern western region, means the Rajasthan region. But suppose we are the policy maker is planning to install the power plant near to the thermal power, means definitely 10 to 15% efficiency will be decreased, and the maximum the labor will use for the cleaning purposes. So next one is the result of experimental study 2. Experimental study objective improve the hotspot. So here we can see the hotspot impact of the partial setting on the photovoltaic system. So here we can see the hotspot generation under partial setting condition and its mitigation during the partially setted condition due to the conduction of the bypass diode. Multiple peak in the power versus voltage characteristic are produced, and it makes the maximum power point tracking is complicated. So basically the IV and PV characteristics of the PV cells are non-linear in nature and are function of the several factors like irradiance, temperature, humidity, and tilt angle and wide speed, etc. So under uniform radiation, there is a one unique point on those nonlinear curves at which the PV system operates more optimally and generates the maximum power output, and its unique point is called the MPP, maximum power point tracking. So a bypass diode connected across each sub-panel effectively provide a bypass path for the photo current generated by the illuminated photovoltaic cell. Hence, constant loss of the power output under partially shaded condition. And however, the conducting of bypass diode produces more than one peak, means that is a global peak and local peak. The local and global peak, and this makes the maximum power point tracking more complicated under partially shaded condition, and that will produce the different types of also losses. So here we can say the PV response analysis under non-ideal condition. So So here in the next experimental study, we have considered, suppose three different types of the modules are connected in series, and load is also connected across this module. And suppose that due to the various degradation mechanism, reduction of photogenerated current in photovoltaic PV cells leads to hot spot mean generation, resulting in the serious safety and reliability concerns. So here suppose these three panels are connected in series, and suppose in the third one is the partially shaded. So you can see the IV characteristic for particular first module. So it is coming positive, means suppose PV cell 1, so C1 B1 A1, C1 B1 A1, and PV cell 2, C2 B2 and A2. So it is coming positive. But suppose on the third case, third module is partially shaded, so you can see the curve is means the IV characteristic is coming the negative, means it is the shaded, means these two are treating as the source, but third is treated as the sink. Means when for the operating point corresponding to the here operating line, this line, operating line OB, reverse voltage appear across the photovoltaic cell, means cell third with the current is still flowing in the same direction. When the PV cell becomes reverse bias, it will sink rather than source power and heat up, owing to the resulting power dissipation. And the amount of power dissipation in a reverse bias means photovoltaic cell depends on IV characteristic, which vary widely among cells. And suppose in the reverse characteristic of PV cells, so here another suppose we are tested the module. Here the suppose the 10 cells are connected in series. So here we can see what is the reverse characteristic. So we can see the here the first cell, suppose the PV module were disintegrated for the assessing the shaded cell 1, this cell 1, and terminal marked by the, it is a plus and minus. And suppose it is experimentally tested and found in the simulation, if we are suppose increasing the reverse voltage, means first suppose reverse voltage approximately near to the 0, it is started 0, and it is less than minus 30 volt, means it is minus 10. So what is the shunt resistance? Shunt resistance is approx 10 ohm. But suppose reverse voltage is increasing, means that is a more negative, means it is minus 20. You can imagine what is the shunt resistance is 415.5 ohm. It is simulated, but we can also check the reverse characteristic experimentally. So it is the IV characteristic of the module. It is like this. So reverse characteristic of completely shaded cell is estimated. That is the completely shaded, and what is the PV module rating is 2.5 watt, means maximum peak was used to test module estimated. So here you can analyze, we have analyzed the power loss in the shaded cell exhibit hotspot behavior. So here we can see it is the measure the power loss of the completely shaded cell. So at the normal natural solar radiation is around 824 watt per meter square. The forward IV characteristic of the unshaded cell means acting as the source, means only it is acting as this, you can see it is the less than reverse voltage is less than means 13 volt means higher than more negative means less than means minus 14 minus 15, that will act as the sink. So to determine the power loss in the shaded cell means were reflected as superimposed on the source means forward IV characteristic in the first quadrant means the demand of this cell generated power maximum power is 1.76 watt at the rate of means radiation level is 824 watt per meter square. So finally we have calculated the power loss is 2.98% of the peak power. Means if we are suppose completely shaded, so what is the peak power loss? So here we can see the thermographic behavior of the reverse biased PV cell. The cells were subjected to gradually increase reverse bias with the simultaneous thermal monitoring, causing increases the power loss in the inspected cell. So here it is the suppose under normal condition. Here we have captured this image through the thermographic camera, fluke fluke thermographic camera, and maximum temperature is 25.8 degrees Celsius. But suppose after the setting of the particular cell, you can imagine under the reverse bias condition, the thermal response of the shaded cell maximum temperature is 80.4 degrees Celsius. Means the avalanche breakdown in type 3 means third cells are shaded is observed to occurring at range of minus 13 to minus 18 volt for PV cells. If the voltage is coming between this range, so definitely that will increase the temperature around that will reach around the 100 degrees Celsius. The reverse voltage that acts across the PV cells under mismatch condition matches exactly at which avalanche breakdown occurs, and on gradual application of the reverse bias within 3 minutes, means within 3 minutes the temperature increase at the highest value of 80.4 degrees Celsius. And if the suppose importance of the reverse breakdown, avalanche breakdown voltage, so how we can calculate the reverse voltage? So it is basically the reverse voltage across the shaded cell can be calculated through this formula. So suppose we are having 60 cells. So here we can see, suppose we have standard modules are connected in series, and for particular this module, suppose the 60 cells are connected, and suppose we can bifurcate 60 60 60 means 20 cells in a subsection, and 3 diodes are connected in between 10 cells. So we can just calculate the reverse voltage. Reverse voltage, maximum reverse voltage is equal to means 20 cells are connected in a subcell. If the suppose module in the 60 cells, so in a subsection 20 modules are connected. 20 minus 1 into zero point 0.6. 0.6 is, you know, the VFJ is 0.6. So 0.6 plus 0.5 is equal to 11.9 for the 20 volt. It is the standard normal voltage is 20 and reverse voltage is 11.9 for 60 for a module. Suppose 60 cells are connected, and suppose in place of the 60 cell we can just consider 72 cells. Then what is the reverse voltage is 14.3 volt. And suppose we can just change the cells, mean number of cells. Suppose we are just changing from 70 to 96. So what is the reverse voltage is now at 19.1 volt. Means the avalanche breakdown is observed to be occurring at minus 13 voltage to the minus 18 volt. So it is coming, these two are coming in the second criteria, means avalanche breakdown minus 13 to minus 18 volt. So it has some we have just experimentally validated. So suppose a string, three modules are connected in series. Experimental setup for assessing the thermal reliability of the module under partially shaded means 3 cross 1, means three modules are connected in series. So here we can see it is the one controller. To suppose in temperature is suddenly within 3 minutes is rising 80 degrees Celsius. So we have just suggested a controller there. Suppose we can cover the suppose cells. There are no change in the temperature, mean there will no effect on the temperature. So it is the controller. So so you can see here the experimental setup. Suppose 3 cross 1 PV string. The development experimental setup consists three identical PV module mounted on the same supporting frame, aligned in the same direction, at the same inclination. The thermal imager is used to inspect the thermal behavior of the mismatch module. So the 3 cross 1 PV string was examined under the effect of the artificial shadow of wearing. SR means one cell shaded, means what is the mismatch loss is the around 2.5 2.77%, and two cells means 5.55% under the same operating and ambient condition. Setting setting ratio means SR can be calculated number of shaded cells divided by total number of cells in the module into 100. So here experimental setup 2, here we have considered 3 cross 1. 3 cross 3 means three are connected in series, another is also parallel, another is parallel, and it is the controller, means it is a um, controller can be protect or can be maintain the normal temperature. So here the development experimental setup consists of 9 identical PV module mounted on the same supporting frame. So that is the same, means the artificial shadow in fact module was examined with both standard bypass diode and integration with the proposed HMMC. The thermal imaging measurement of the shaded cell were performed to quantify the impact of the mismatch effect in the PV system under examination. And here we can see the specification of the experimental platform. So here the PV module Excite means it is the company means EIL 40, and what is the parameter? The maximum power is value is 40 watt, open circuit voltage 22.18, voltage at MPP is 18 volt, current at MPP 2.22, short circuit current 2.40, number of cells 36, means 9 into 4. So tolerance plus 0 to 5 means thermal imager specification. It is a fluke, means parameter, detector resolution, thermosensitivity, accuracy, frame rate, and these are the value of the thermographic. So here we can see the proposed HMMC means circuit. So which we have just suggested to protect or to improve the reliability of the module. So we have just connected two MOSFETs. One MOSFET is connected in series with the module, and another is the connected across the module. So here the connector is really between the module and the load, and MOSFET 2 connected across the module mean the event of the partially sided condition Q2 is driven into conduction, offering near short circuited path across the affected module, thus providing a bypass. And it is actual proposed SMMC circuit and proposed to bring the temperature of the shaded cell well within the safe limits. The reverse voltage imposed on the shaded cell should be pushed sufficiently low to prevent the mismatched PV cell from reaching the avalanche breakdown. So basically, it is the under normal condition, if the string current is equal to the drain source current, so here it is the generation from only two PV sources. One is the bypass through the um, MOSFET, bypass through the MOSFET. So experimental setup for selecting the appropriate switches for the proposed SMMC circuit to reduce on state power loss of HMMC, a meticulous selection of the switches from a variety of the available MOSFET rating is carried out through extensive initial experimental analysis on a laboratory setup before their deployment into the operation. So MOSFETs having low on state drain source resistance is very low, means so we can just see what is the scenario, means this is the very low because it is connected in series. If suppose it is the resistance is high, then that will increase the temperature of the panel. So we can just we have selected the lowest resistance. So we have just experimentally tested first means different types of the yeah, MOSFETs, and here the characteristic between drain current to the gate source voltage, and other is the resistance to the gate source voltage to the source voltage. So experimentally investigated MOSFETs. So here, so what is the result of the result and discussion of electrical measurement? So here we can see the measurement of electrical characteristic of 3 cross 1 PV string. First one is the power voltage characteristic. Second one is the current voltage curve. Third one is string voltage. Means here it is basically the suggested means new technology was non-sided, partially sided, and bypass diode. Suppose it is a normal condition, but it is a without bypass diode. There is a no bypass diode is connected, but it is here you can see bypass diode and this new technique. So it is increasing the power level, means enhance the power if we are comparing both the parameter. So here we can here it is just and a similar pattern in the IV characteristic, but so the thermal inspection and key measurement were performed for the 3 cross 3. The series parallel configuration PV array was also tested to evaluate the HMMC performance. Different operating condition means normal, unshaded. So here we can see partially shaded number of bypass means one cell shaded. Agar suppose one cell is shaded means HMMC of means third one is the bypass with standard bypass diode means two cells are shaded, and fourth is bypass with the proposed HSMC is greater than one cell sided. So here we can say hotspot is spawn region one cell. Suppose one cell is sided, and suppose one cell is sided, the current IV current is almost zero. But suppose two cells are shaded, so you can see here the what is the characteristic of IV current, means current is increasing. But in my case, you can see the current is tremendous change in the current. So the bypass diode does not activate it if suppose we are shedding one cell. Here we can see the level of the current. So in the similar pattern, suppose 3 cross 1, 3 cross 3 means measure electrical characteristic of 3 cross 3 series parallel PV array, mean power voltage, current voltage. So similar pattern we can see here, the similar pattern. Means a conventional bypass diode completely failed to bypass the said affected module under one cell shading, and the shaded region represents the hotspot prone region under one cell shading. Means this circuit means HMMC is more effective to increase the reliability and enhance the power. Here you can see power and reliability both are increasing, but we can just in next PPT we can just check the temperature of the panel. So here experimental analysis of different rated PV modules. The three cross one PV string were selected, each comprising of different rating of module. The description of the same is given below. Here it is the key parameter values and modules. So here you can see difference means just we can check the bypass path and voltage characteristic, what is the current, and here it is basically the different types of the bypass diode current, and it is suppose the 50 watt. So we have one cell and two cell, just we can check. We have checked. So experimental analysis of different rated PV module. So 3 cross 1 PV string were selected, each comprising different suppose one cell is setting on the module, then the temperature will suddenly increase, but there is no bypass through the diode. But the shaded cell region represents the hotspot prone region under one cell. Means under one cell setting, the temperature also increases for 50-watt rated PV module having the single integrated bypass diode, confirming the inadequacy of bypass diode under low setting event. So in the next case, dynamic response of the analysis of the PV system. So here we can see the suppose we are it is the power is in the normal condition. Suppose power is in normal condition, it is captured in the DSO through the DSO. So you know the if the panel is totally clean, there is no setting effect. So you can see it is the, and after 12 seconds the system operates the normal condition to the onset partially shaded one cell completely shaded occur at t is equal to 12 seconds. After 12 seconds you can see what is the voltage is suddenly decreasing, current is decreasing, and power is also decreasing. After 22 seconds after 22 second bypass diode gets activated, means under 2 cell setting. After 22 cells are setting here, after 22 means second means 2 cells setting, and provides the bypass path to the string current, you know. And after 32 second means it is suddenly decrease, means if we are suppose setting 2 cells, the power is decreasing. After 32 second, is reduced to 1 cell again, and proposed we have just started at this position, we have started the circuit, HMSC circuit. It is suddenly increase the current, increase the power, and increase the voltage level, means here it is increasing the power. And what is, we can see the what is the effect on the, what is the effect on the temperature. So if we are here suppose considering the 3 cross 3 series parallel photovoltaic module. So interestingly, bypass diode activation starts only for the if the greater than 2 cell setting condition, thus exposing the mismatched cells to thermal degradation over time for low means is greater than 2 cell setting condition, and hence may initial irreversible failure of the module. So same pattern you can see if we are using the HMMC activation, the power is enhancing, and similarly current is also enhanced. If suppose we have just switched on after 32 seconds, it will reach the normal condition. So here we can just estimate the power loss in the 3 cross 1 PV string. So it is the characteristic, and experimental results reveals that the maximum power point that P means bypass means power loss is reduced up to the 88.6 and up to 89.2% under 2 cells and 3 cells setting respectively after the application of the proposed SMMC. And next is basically last, we can just check the reliability of the thermographic. Suppose we are here considering the 3 cross 1. So you can see the under normal conditions, the maximum temperature of the middle panel means middle panel. Suppose 3 panels are connected, so we have just measuring the in middle second panel means the middle panel. So PV string means first, if we are using HMMC, so what is the temperature of second module is 42.4 degrees Celsius, and PV string suppose we are using the bypass diode, so what is the temperature? 42.7%, just slightly, there is no change. But here we can see under 1 cell shaded condition, the maximum temperature of the middle panel for if we are using the bypass diode which is already installed in the module, it is reaching 99.5 degrees Celsius. But suppose in place of bypass diode, suppose we are using this circuit means in place of the bypass diode using this, so it is reducing up to the 45 means it will reach approx the normal condition means 45 degrees Celsius. So what is the means in a previous slide we can say here the power is enhancing, but suppose we are using the HMMC circuit, so power is enhancing as compared to diode, and also the temperature is decreasing as compared to bypass diode. So similarly you can see if the 3 cross 3 module, so similar pattern here you can see the if temperature is reaching up, maximum temperature is here is 80.6%. As on the shading area is increased, the thermal behavior of the both the shaded module have similar nature, and bypass diode completely fail under low shading conditions, posing a serious threat to the system reliability. So conclusion, the present work proposed an alternative and improved solution to address the inadequacy of the bypass diode for HS means mitigation, and novel HMMC circuit alleviates the circuit based on the dual power MOSFET configuration, which can be easily integrated with any number of series connected PV cells is proposed. And the next is integrating the proposed HMMC with 3x1 PV string and 3x3 series parallel photovoltaic array resulted in maximum power enhancement of 5% and 2.42% respectively when shading increases from one cell to two cell. But under low shading events, means less than one cell, means the maximum temperature of module protect using bypass diode was 119.16% and 54.11% higher compared to proposed HMMC when tested on 1x1 and 3x1 PV array. Additionally, the power loss in the bypass path was significantly reduced to up to 88.65 and 89.82% under two cells and three cell setting with the proposed hotspot mitigation circuit. So basically, these are the conclusions. Thank you.
Thank you, sir. Once again, I would like to extend my sincere gratitude to our expert, Professor Vinod Kumar Yadav, for taking the time to be with us today. Thank you, sir.
Sir,
Participants, if you have any query, please ask.
Dr. Sovaram, I want to ask a small query.
Yes,
Dr. Vinodji, good afternoon.
Good afternoon, sir.
सर वो मुझे एक चीज आपसे जाननी थी कि when there is a dust is falling on the sun panels, so it is reducing the electric generation capacity of the sun panels as you discussed.
Suppose, sir, we have here consider 4 different type of dust.
Yes, sir.
One dust is normal dust जो हमारे घर के आसपास मिलता है.
We are talking about the actually normal dust, wind blown dust जो normal dust होती है.
तो उसमें क्या है कि सर अगर हम जो हमारा राजस्थान में नॉर्दर्न वेस्टर्न रीजन में पड़ता है तो वहां पे जब एयर आता है, हवा आता है सर, तो वो साफ हो जाता है, तो उससे कोई ज्यादा इफेक्ट नहीं पड़ता. वो नॉर्मल एफिशिएंसी जो अप्रॉक्स 21 टू 25 डिग्री 21 टू 25% एफिशिएंसी वो रहता है.
अच्छा.
लेकिन जो हमारा घर के आसपास है ये इसकी एफिशिएंसी लगभग 5 to 6% कम होती है,
रिड्यूस हो जाती है.
हाँ, कम हो जाती है क्योंकि सर उसका क्लीनिंग उतना हम नहीं कर पाते हैं.
अच्छा.
लेकिन जो कार्बोनेसियस जो थर्मल पावर उसका वेट जो वेट होता है वो बहुत कम होता है.
अच्छा.
और जब उस पे सुबह ओस पड़ता है ना तो उस पे चिपक जाता है सर.
अच्छा.
हाँ, तो उसकी एफिशिएंसी 15 to 20% टोटल जितना जनरेशन हो रहा है उसका बहुत ज्यादा, मतलब 15 to 20% कम हो जाता है.
अच्छा.
इसलिए लोग रिकमेंड नहीं करते हैं कि उसके आसपास इसको लगाया जाए.
अच्छा. नहीं, जैसे हमारे यहाँ क्या है कि ये इसमें क्या है, जितना भी सन पैनल्स लग रहे हैं सबके ऊपर डस्ट जम जाती है. तो अब इसका क्या तरीका है कि इसको वी शुड क्लीन इट रेगुलरली.
वी शुड क्लीन द पैनल, अदरवाइज तो उसका कोई जनरेशन का ज्यादा नहीं है, क्योंकि ना इसका जो वेवलेंथ इंटेंसिटी ऑफ द रेडिएशन, इसका जो है सर उस पर प्रॉपर नहीं पड़ता है, क्योंकि इसका जो है वो अगर दोपहर होगा, जैसे टेम्परेचर बढ़ेगा, सपोज टेम्परेचर इज इंक्रीजिंग, एट दैट टाइम द जनरेशन विल बी डिक्रीज। उस समय हमारा क्योंकि टेम्परेचर नॉर्मल टेम्परेचर बढ़ जा रहा है, जो हमारा सरफेस टेम्परेचर वो बढ़ रहा है तो, लेकिन अगर आप देखेंगे 9-10 बजे अगर क्लीन पैनल रहेगा तो उसकी एफिशिएंसी, उसको सबसे ज्यादा जनरेशन मिलता है। अच्छा, क्योंकि उसका वेवलेंथ बहुत हाई होता है सर, हाई होता है वेवलेंथ। तो सुबह के टाइम बहुत अच्छा, लेकिन जैसे हमारा दोपहर होगा लगभग 1 बजे के आसपास, हमारा जनरेशन सुबह के कंपैरिजन में कम हो जाएगा। तो इट मीन्स कि जो रेनी सीजन होता है, रेनी सीजन में जब रेनफॉल होता है तो ये साफ हो जाते होंगे। हाँ, वो बहुत अच्छा उस समय जनरेशन, उस समय अच्छा जनरेशन होता होगा। हाँ, उस समय एकदम अच्छा जनरेशन होता है। उस समय हमेशा आप देखेंगे बहुत कम लाइट रहेगी ना, आपको पता नहीं होगा, फिर भी बहुत अच्छा जनरेशन आता है। अच्छा, तो इसका मतलब ये चीज है। और दूसरा ये कि जो सीजन वाइज जो है, अगर हमारा टेम्परेचर, क्योंकि हमारे यहाँ फ्लक्चुएशन ज्यादा होता है, हमारे हम जिस रीजन में यहाँ रहते हैं एनसीआर में, तो समर में बहुत ज्यादा टेम्परेचर होता है डे टाइम में, और विंटर में नॉर्मल टेम्परेचर 20-22-15 डिग्री जो रहता है डे टाइम में, तो शायद ये विंटर में ठीक ठाक जनरेशन होता होगा और समर में डे टाइम में कम होता होगा, सुबह अच्छा होता होगा। सर ये अगर क्लीन पैनल है मेरा, तो जिस समय हमारा टेम्परेचर कम होगा, अभी मैंने ये कैरेक्टरिस्टिक बताया था। जी हाँ, बताया आपने, वही इसलिए मैं पूछ रहा हूँ। हाँ, तो जितना कम टेम्परेचर होगा, अच्छा, उतना ज्यादा हमारा जनरेशन होगा। ओह, अच्छा। हाँ, क्योंकि उसमें हमारा हाईएस्ट करंट कैपेसिटी हो जाती है, ठीक, इसलिए पावर आउटपुट हमारा मैक्सिमम होने लगता है। ठीक सर, थैंक यू सर, यही पूछ रहा था सर। थैंक यू सर। एनी अदर क्वेश्चन? So,
participants, have you any question? Okay, thank you, sir.
So, thank you all for your time and attention throughout this presentation. Basically, special thanks to Dr. Nidhi Pal Singh ma'am and Dr. S.C. Thakur sir, and Dean School of Engineering, Dr. Kirti Pal ma'am, HOD, Dr. Ombir Singh, Ansari ji, and other faculty member. Thank you. I appreciate the opportunity to share these insights with you and look forward to any future. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you so much. Can I leave?
Yes, sir.
Thank you.
Okay, thank you, sir.
Thank you, sir.